All right, we're going to look at second order differential equations. I am starting with assuming everyone already understands the infinitesimal generator. I'm putting it in here, and I've put in prolonging it to the nth order because we're going to build, right? So I wrote it all down first so everyone can just start taking it down. If you need to pause the video, clearly that's the beauty of having it in video. You can just pause and take things down as you need to. But I'm just going to go through. I'm not going to pause to let you write. You can pause me as you're watching. Okay, so we have the generator and we have what these prolongations are. So these are our prolongations here with eta. So we use eta as what our prolongations are, and then we put the superscript in brackets so that we don't confuse it to mean a power, because it's not a power, it's just the degree of the prolongation. Okay, so because we're doing second order, we only need the first two, and so I've written them out. I can do another video where we work them out by hand. It's lengthy, but it's good to know how to do because there are a lot of textbooks that are older and that have a few small typing mistakes, and then it's nice if you can figure them out yourself because then you can catch those few little mistakes that are there. Okay, so these are the two prolongations, and then we have to apply Lie's invariance condition. And so I've just kind of, and I wrote this really messy, I'm sorry, but for the function f, right, so if it's any differential equation, it can go up to differentiating y to any order, so that's why I've got my dyn. So, and I've put these ellipses here. I'm really sorry, they're kind of messy. This is not my best work. So there we go. And so the condition is that if we apply our generator to that function, it will equal 0 when the function is 0. And that's essentially what we are going to do. So I'm going to start off with like a really simple one, and then I'm going to do another video later on, and I'll put that up with a little more complicated one. But that one I'm going to kind of leave blanks, and hopefully you guys can work them out. So here we want to apply our generator. So we only have to go to the second prolongation of the generator because we only have a second order differential equation. So when I do that, so if we look here, our generator is going to say we need to take xi multiplied by, sorry, I'm like finding a nice highlighter. Okay, so we want to go xi multiplied by the derivative in terms of x, partial derivative in terms of x. So if I look at my function, though, there isn't anything like that, right? I don't have any term that is a partial derivative of x. So what we're going to have is, and I'm going to start writing this here. So we're going to have xi times 0. Then we have to take eta times partial derivative in terms of y, but we don't have any of that either. So it's going to be eta times 0. Then it's the first prolongation times the partial derivative in terms, so first derivative, right, of y. But there isn't any first derivative of y in here either. So I don't have no y primes. It's just y double prime. So then now we're going to get to the last part where it says, okay, so then we have to add, and then that second prolongation times, if I take the derivative in terms of y double prime, then that will be 1. Okay, so I hope that makes sense. Now I sub in what all my prolongations were. So I have all these zeros, I don't need to write them again, and it's essentially just the second prolongation times 1, which is just going to be the second prolongation. So I'm just going to put that in here very quickly. And I like to just put my powers outside if I'm using prime. as to denote my my derivatives. It just makes it look a little easier to read, at least for my brain. Okay, so that's what we get, right? And so Lee's invariance condition says that what we have is going to equal 0, and my f is y double prime. So when second derivative 0, this whole situation will be 0. That means if I apply that, so let's just add a little therefore here. So we're going to have this equals 0. Oh, that's very ugly, 0. Equals 0. And that's because we have to substitute that y double prime is 0, which means this whole thing is going to become 0, right? And so then that just falls away from the whole scenario. And so that's what we have. And now what we need to do is we have to get our monomials, and they are found by looking at what are the coefficients of my powers of y prime. Okay, so what I get is we equate all the coefficients of the similar powers of y prime, and we set them to equal 0. Okay, so those are my equations. I'm going to number these. Okay, so from these equations now, we are going to try to determine my eta and my xi. So let's see what we can do. So from 4, that's what 4 tells me. So if I integrate once with respect to y, I'm going to get some function in x. And then if I integrate again, then it's some function in x times y plus another function in x. That's what I'm going to get there. And then what I can do with that is I can now, using that, so I'm actually going to call this equation 5. And I'm going to find the other derivatives, so differentiating them in order to fill in anything that I have in my other equations, so in equations 1, 2, and 3. So I'm just going to write here from 5. We are going to have, with respect to x, we can also get with respect, we already have with respect to y, we can get with respect to, that's just, I think we need that one as well. Yep. So we can do that. And then we will also go xy. And so that's what we're going to have there. So with those, now we're going to see what we can do with them. So let's look at equation 3 now. So equation 3 tells us that. And which means I can then say and what I'm going to do is I'm going to number these as well. Well, that was, okay, so that's 6. 7, 8. So we can then say that this is equal to because we are going to substitute 8 in there. And then so we will now have a means to integrate to get my eta. So let's do that. So integrate once in terms of y. And then another sorry, that was wrong. Okay, so that's what we're going to have there. And so now I have some form of xi and eta, except I have all these like functions of x. I have a of x, b of x, c of x, d of x. Now I need to figure those things out. So now I'm going to use my other two equations, so equations 1 and 2, to do that. So what I'm going to do is I'm going to pause here. No, I still have time. Okay, so I'm looking at the clock and trying to see how much time I have. Okay, so let's now look at putting those into my equation. So I'm going to number these again. I think I'm just going to number, I'll just number all of them. So okay, so once I have that, I'm going to substitute all of that. I'm going to substitute things into equation 2. So equation 2 had now I haven't really shown the differentiation, so I think I'm just going to do that just in case. Okay, so from 11, we can now, we're going to get one more. We're just going to get actually 2 more. So we're going to go so if I differentiate once in terms of x, I'm going to get And then if I go twice, and then we will also, from 10, if I just take 10 and I differentiate with respect to x, okay, so that's what I'm going to have. And so now I'm going to look at equation 2. So equation 2 said this. And so if I put that in, then I'm going to have so what we've done here is we have substituted, I need to call this an equation, so this is 12, 13, 14, 7, 14, and we are substituting in 7. And so that's what we get. And so we can simplify this. Okay. So this I'm going to call 15. We can also take equation 1 and from equation 1, which said that we just sub in 13. And now we have and this is now 16. So from 15 and 16, what we do is we equate powers of the coefficients of the powers of y, and then we're going to use those to solve. So it's like long, but it's not hard math, it's just a lot of calculating. So I'm going to put like a little what we're doing here. I'm not going to write it like that. Okay, so what we get is we are going to get and we also get so that comes from 15. And so this I'm going to call 17, and this I'm going to call 18. So I can take 17 and I can now integrate to get what a of x is. So once will just give me a constant, and then once more I will get that. Okay, so that's like one piece. Now I can't do much with 18, like it's just, I'm just there. Okay, so we will wait with 18, and now we're going to look at 16. So from 16, we don't need to worry about the a triple prime because we already have a. So we're just going to leave that alone. And we're going to move on to look for C and D. Now, remember, I needed C in 18. That's why I left 18, because 18 I had like B of x and C of x, and I can't marry those two together and do anything with them. But if I have C by itself, as I do here, now I can try to do something. So this I'm going to call 19. And this I'm going to call 20. And I think what I'm going to do is I'm going to leave it to you to try to get C of x, D of x, and by having C of x, so once you have your C, right, so from this you're going to follow what I did above and then get your definition of C of x. And I want you then to push that into 18 and get me B of x. And once you have those, so C, D, B, once you have those, if you want, you can either put them into the group chat or you can send them to me privately. You have my number on the group chat, and I can then annotate and correct or tell you, yes, you're on the right track. And what I will do is later on this evening, my time, which is probably early in the morning, your time, I will then post like a video explaining the rest of it, and then you will see how we get all of that married together to then have our symmetries. I hope this is helpful, and I hope it's not just, telling you stuff you already know. But yeah, and then I'm going to do another video with a more complicated one, because it's kind of simple when you're like, oh, this whole thing becomes zero. So I'm going to do something with another second order differential equation afterwards, but I figured this was a good start.